Today we're going to discuss about effects of relativity. Look at this picture here. We have a aeroplane, dog, and a satellite. Each one of them are moving with different speed. According to Galilean relativity, no matter what the speed they're moving with, the time measured by them will remain same. And we say the time is absolute, one clock for all. But according to Einstein relativity, we know the time measured by each object with respect to the speed they're moving with decides the time they measure. And we say the time is relative, means each object one clock. Let's build a clock, and this clock is going to be built using a photon, which is oscillating between the two plates. As soon as the photon completes one oscillation, it is equal to 1 second. I'm going to fix these two clocks inside the train, one outside the train, and you can see the time measured by both the clocks are obviously going to be same. But if in case the train is moving with constant speed, you can see the photon inside the train has to travel diagonally, causing it to travel more distance, means longer time period. Therefore, different time is going to be measured by the different observer. That means the time ticks differently in each frame with respect to the other frame. And we call this effect as time dilation. Look at this picture. The clock is inside the rocket, which is moving with constant speed. Now, because the clock is at rest with respect to the moving frame, the change in position of this clock with respect to that frame is zero. And we call the time measured by the moving frame as the proper time interval, which is the time between the two events that takes place at the same point in space. What does it mean? Because you know the clock is at rest with respect to this moving frame. So if it was at a distance x while the rocket was started from the Earth, it remains at the position x from the origin, even if it is far away from the Earth, because the clock is at rest with respect to this prime. And we consider the change in position of this clock delta x prime is zero. Then what will be the time measured by from the person on Earth? Like, what is the time measured by the person inside the rocket? We call that time as the proper time interval because the clock is going nowhere. The clock is at rest according to this observer. Therefore, he is measuring the proper time. Then what is the time measured by the person on Earth who is at rest? So I'm going to use this condition delta x prime to be zero and substitute in the formula that we've learned that delta t is equal to gamma times delta t prime plus v delta x prime over c. Since delta x prime is zero, it gives delta t, which is the time measured with respect to the frame of Earth, is equal to gamma times the time measured with respect to the rocket. So you understand that the time measured from the Earth is gamma times factor larger than the time measured with respect to the moving frame. And we call this formula as a time dilation formula. The second relativistic effect is called length contraction. Say a ruler is fixed inside the rocket and rocket is moving with constant speed. And you can see the ruler is at rest with respect to the moving frame S prime, whereas that it is in motion with respect to the frame S. I'm assuming the frame S to be the Earth and moving frame S to be the rocket. The person on Earth is, I'll call it as observer A, and the person inside the rocket I'm considering to the observer B. So the observer B has to measure the length of the ruler by knowing the initial position of the ruler and the final position of the ruler at any point of time. Means he can measure the initial position at 9 o'clock and he can measure the final position at any other time, say 9:30. Why? Because ruler is going nowhere for him, because ruler is at rest with respect to the rocket. But that's not the case for the person on Earth. The ruler is moving away for him. Since the ruler is moving away from him, since he know that the ruler is moving away from him, he has to measure both ends of the ruler at the same time. Means if he is measuring x1 at 9 o'clock, he has to measure x2 also at 9 o'clock. That means the time difference for him to measure both ends is zero. That means the time difference to measure both ends with respect to the person on Earth is zero. But whereas the time difference for the person on the rocket to measure both ends x1 and x2 may not be zero because he can measure both ends at any point of time because the ruler is going nowhere for him. And the length measured by the person B is considered as proper length. Means it is special. Why is this length special? Because it is measured in a frame of reference where the ruler is at rest. Okay, sir, I understood that whatever the length he has measured is the proper length, and it is understandable because ruler is not moving anywhere for him, because ruler is at rest. Whatever the length he is measuring is the proper length. But what about the person on Earth? Is he also measuring the proper length? The answer is no, because he will see the relativistic effect causing the ruler to contract, and we call this phenomena as length contraction. I'm going to use this condition that delta t is zero and substitute in the formula of Einstein transformation that delta x prime is equal to gamma times delta x minus v delta t. Since we know that delta t is zero, it gives us delta x prime equals gamma times delta x. What is delta x prime? It is the proper length denoted with L naught. And what is a delta x? It is a length measured with respect to the stationary observer from Earth. And that gives us the final formula L with respect to the stationary observer is equals to proper length divided by gamma. And since the proper length is being divided, that means the length measured by the person on Earth will be shorter by gamma times. Let's see this relativistic effect in real life by using a muon experiment. Say when you bombard a proton to a carbon-12, it finally produces a particle called muon, which moves with speed of around 0.98 c and has a half-life of 1.6 microseconds. I'm going to keep about 100 muons at a height of 480 meters above the Earth. And then how long do they take to travel this distance? With the speed of 0.98 c, it will take 1.6 microseconds, which is equal to one half-life of muons. That means about 50 muons should reach the surface of the Earth. But that's not true experimentally. Experimentally, scientists found that about 87 muons are reaching the Earth's surface. But how is this possible? So, according to special relativity, the time in the muon frame of reference is dilated. Because the time is increasing, the half-life gets longer. So, let's calculate how much half-life is with respect to the muon frame of reference. So, the gamma is 5 by using the speed is equals to 0.98 c. The delta t is a half-life measured from the Earth reference, and delta t naught is a half-life measured from the muon reference, which is 1.6 microseconds. And you know, delta t naught is called as proper time. So calculation will give delta t as 8 microseconds. Using the formula delta t is equal to gamma times delta t naught. We get n is equal to 87 muons. Let's calculate that. We know the formula n is equals to n naught, which is called initial amount, into e to the power of minus lambda t, where lambda is equals to natural log 2 divided by t half. Now, which is equals to natural log 2. What is the t half now? According to this relativistic effect, it is 8 microsecond. And how long does it take to travel down? The time period is 1.6 microsecond. So substituting all this value, you will find n is equal to 87 muons. Now we'll see, is this true with respect to the length contraction? For example, if this is Earth and that's the position x, the length measured by the observer between x1 and x2 will be considered as the proper length and not. Why? Because x1 and x2 is going nowhere. But since the muon is traveling closer to the speed of light, the x1 is moving away from it while it is moving down, and x2 is getting closer to it while it is moving down. That means this length L will be contracted for the muon while reaching the Earth. So by using the formula L is equal to L naught by gamma, it gives contracted length to be 96 meters. Then how long does the muon take to travel this 96 meter? It will take just 0.32 microseconds. With a half-life of 1.6 microseconds, we can calculate the value of n, which is also going to give me 87 muons. How? Again, I'm going to show you the calculation where n is equals to n naught into e to the power of minus lambda t, where lambda is again natural log 2 by t half, but this time the t half is the same amount of half-life. We're not talking about the time dilation, we're talking about the length contraction. So which is 1.6 microseconds, and substituting in the above formula for the value of lambda. And what is the t here? It is nothing but how long is the muon traveling before reaching the Earth's surface? It is traveling only for a time period of 0.32 seconds. So we'll substitute that 0.32 seconds in the place of t. And finally, we'll get n is equal to 87 muons. Finally, the results from the muon experiments agree with those predicted by the Lorentz transformations. The next one is simultaneity. Events that are simultaneous for one observer and which takes place at different points in space are not simultaneous for another observer in motion related to the first one. Means if you consider that event is simultaneous for, like, let's say the event E1 and event E2, both the events occur at the same time for one of the frame S. Those two events may not be occurring at the same time for other frame S prime, which is moving at constant speed v. On the other hand, if two events are simultaneous for one observer and takes place at the same point in space, they're simultaneous for all the other observers as well. So in the previous case, I consider event E1 and E2 to be occurring at two different points in space. Now I'm assuming that both event E1 and E2 occur at the same point in space. Then, because E1 and E2 is simultaneous with respect to the frame S, it will consider to be simultaneous for any other frame which is moving with speed v. Let's take an example, A and B, from which the photons are emitted. There's an observer in the middle, and we'll label it as T, and there's observer outside the train, which is labeled as G. The photon emitted from A is at the position x1. The photon emitted from B is at the another position x2. So even E1 and E2 are not occurring at the same position. But according to the observer T, both the photons are emitted at the same time. So it is simultaneous event according to the observer T. But will that be simultaneous event according to the observer G? The answer is no. That is what the simultaneity topic is all about. Because the events are not at the same position. But interestingly, as soon as the photons reach the observer T, both the photons are reaching at the same position. The final event E3 is occurring at the same position. And if it is simultaneous for the observer T, it is simultaneous for any of the other observer. That means the event E3 is simultaneous for observer G as well. Which signal was emitted first according to G? I mean, wait, sir. You only said both the photons are emitted at the same time. Then why are we saying that which signal was emitted first? Because don't forget, since the event E1 and E2 are not at the same position, it is considered to be simultaneous for the observer T, then it is not simultaneous for the observer G. That means the signals emitted from A and B are not happening at the same time. Means one must be emitted first, other must be emitted later. So question is, which signal was emitted first? And the answer lies behind in which direction is the train moving. So you can see the train is moving with constant speed to the right. Because this train is moving to the right, the photon has to travel a longer distance to reach the observer T. And the photon which is emitted from the B has to travel a shorter distance to reach the observer T. Because the photon from the observer from A has to travel a longer distance means it will take a longer time. But wait, both has to reach at the same time. And that can only be possible if the photon from A has emitted first, so that it can travel and reach T at the same time as the photon emitted from the point B. And that's all about simultaneity. In the next class, we'll do space-time diagrams.